everyone, my name is Jonathan De Luna Rodriguez, Motor Control Applications Engineer here at Corvo in the Power Management Motor Control team. This is the Motor Bring Up and Tuning chapter for Sensorless FOC. Our goal for this chapter is to bring up a motor using Sensorless FOC and aim for a stable, repeatable tune. This is part 1. This part we will enter the minimum required parameters needed for first motor bring up. The more accurate these are, the less hassle in the following steps. Here is the workflow we'll follow in this chapter. First, we will enter the required motor parameters and system limits. Then we will get the first spin using open loop align and go. Next, we will transition into sensorless estimator for closed loop, followed by a tuning step-by-step using torque mode first, then speed mode. Lastly, we will save a motor profile so you can reload a known good setup. For this video, we're doing step 1 only, so let's get started by heading over to the FOC GUI. Okay, so here we have the PAC FOC GUI. We will first go to the config tab. The config tab is the main area we'll focus on in this video. In this section, I'll highlight all of the required parameters and I'll give a brief explanation of each one. The parameters you'll need is the phase winding resistance, the phase inductances LD and LQ, the number of pole pairs, the nominal speed and maximum speed, the maximum current, maximum peak current, and the overcurrent peak limit. As to where to find these values, your first reference should always be the motor's datasheet. If the datasheet does not include these parameters, we recommend measuring them with an LCR meter. And as an alternative, you can also use Corvo's FOC AutoTune feature, which estimates these values automatically. Later in the video, we'll walk through how to measure the parameters using an LCR meter, as well as how to use the AutoTune feature step by step. Okay, so the first required parameter is the motor phase winding resistance and inductance LD and LQ. The GUI expects these values to be per phase. Most motor datasheets give line-to-line values, so to convert, you'll use the following. Per phase is equal to line-to-line divided by 2. So if the datasheet gives you a line-to-line resistance or inductance, divide by 2 and enter that per phase value in the GUI. So these R and L values are very important because the firmware uses them internally. They affect how the algorithm predicts voltage and current behavior, and they later influence the estimator coefficients and overall control loop performance. Another thing to note is that the GUI expects the inductance values in microhenry and resistance in ohms. I'll be entering my motor's parameters as we move along. I don't have a motor datasheet, so I use an LCR meter to gather the inductance and resistance values. So I'll go ahead and type it here. And this is in microhenry. And now resistance. Next is pole pairs. Pole pairs is mainly used so the speed display in the GUI is correct. That is on the left side here. You can temporarily leave it at 1 for now, just so you can move forward. We can figure out the real pole pair value later during the open loop video by running at 1 electrical hertz and timing a mechanical revolution. Once you know the relationship between the electrical cycles and mechanical revolutions, you can back calculate the pole pairs. We will show that step when we get there. For my motor, it is 7 pole pairs. Moving along to the next parameter is speed. A quick reminder on units for speed here in the config section of the GUI. These fields are in electrical hertz, not RPM. So if your motor datasheet gives you RPM, convert using the following equation. Electrical hertz is equal to the RPM times pole pairs divided by 60. The first speed parameter is the nominal speed, which is your normal operating reference. Think of it as the speed you expect to run at typical conditions. Nominal speed is used as a reference point in several places such as the estimator and tuning settings. For my case, my motor is a KB 335 rated motor, which is about 6,700 RPM at 20 volts. Using the following equation, it gives a normal operating speed of 780 electrical hertz. So that is exactly what I'll put on the nominal speed, 780. Next parameter is your maximum speed, as shown here. It is your hard limit. This is the speed you do not want to exceed. It is your safety boundary. If you're thinking in simple terms, between nominal speed and maximum speed. Nominal speed is where I expect to operate. Maximum speed is the do not cross line. It is your protection limit. If your commanded speed or your measured speed pushes beyond this threshold, the firmware can limit the operation or trigger a fault. A practical approach is setting high enough that you won't trip it during your early testing, but not so high that you remove your guardrail. For my case, I'll use 880. The next parameter is your OC peak limit. It is your overcurrent limit. This is a hardware protection threshold. This value ties into your overcurrent protection behavior. It is a do not cross line that protects the power stage. For bring up, the right approach is the maximum current is your normal operating clamp. OC peak limit is your hard protection threshold. OC limit should be set above your maximum current, but still within what your hardware can safely handle. For my motor, it had a maximum current of 15 amps. So that is exactly what I'll put for the OC peak limit. And for the clamp, I'll use 8 amps to start. The next parameter is the PWM frequency. The PWM frequency and control timing directly set how often the firmware runs the current loop, estimator update, and PWM updates. Let's set PWM frequency to 20 kHz as a starting point. May not be the most optimal for all applications, but for the first spin, 20 kHz is a good starting point, and we can also adjust later if needed. Next is the control divider constant. We will set the control divider equal to 1. So here, the control frequency is equal to the PWM frequency divided by this control divider constant. So a divider equal to 1 means the control loop runs every PWM cycle. Okay, so that is it. We've entered all the required motor parameters and limits. Next video, we'll briefly go over using an LCR meter, as well as using the FLC auto tune feature to compute the PI gains for the current controller, which is entered in the tuning tab under controllers, shown here. Then we'll move into the open loop align and go to get a smooth first spin baseline.